Conclusion. This lecture presented a summary of mineralogical and chemical composition of raw and surface modified clay minerals and their application in arsenic and fluoride removal from drinking water. From the review, it is noted that properties of the clay minerals such as higher cation exchange capacity in specific surface areas as well as the chemical composition of clay minerals enables them to be used as arsenic and fluoride adsorbents. Furthermore, these physicochemical properties can be improved through intercalation and pillaring, which consequently improves their applicability in arsenic and fluoride removal. Modification of clay minerals does not alter their phyllosilicate structure. However, it improves the basal spacing and specific surface areas of the clay minerals. The modification is mainly through ion exchange between the basic exchangeable cations such Na+, K+, Mg2+, and Ca+ with the guest species. The effectiveness of the clay minerals in adsorption of arsenic and fluoride is mainly influenced by the surface charges, which are determined by the solution pH. At acidic pH, the sorption is higher due to the fact that the surface is positively charged, which influences the sorption of anions through electrostatic attraction. Conversely, at alkaline pH the sorption is low due to electrostatic repulsion. Recently, the attention is mainly on modification of clay minerals to enhance their application in various fields. However, little has been done on evaluating the chemical stability and the cost-effectiveness of modifying clay minerals. As such, future studies should be directed toward evaluating the chemical stability of modified clay minerals, especially those applied for drinking water treatment. Also, studies should elaborate the cost-effectiveness for modifying clay minerals with chemical species. Introduction. The function of a good coating on the metallic surface is to provide a physical barrier, preventing the metal to be in direct contact with the environment. Generally, the main principle to prevent corrosion is to eliminate one of the four main components causing the corrosion process: anodic reaction, cathodic reaction, electrolyte, and electrical connection between the cathode and the anode. Until about 1950, coatings were believed to act as a barrier, preventing water and oxygen to reach the metal. These two species are needed to drive the oxygen reduction reaction, cathodic reaction, that initiates the corrosion process. In 1952, Mayne found that the diffusion rate of water and oxygen in an unpigmented coating is too high. Consequently, he suggested that the amount of water and oxygen arriving at the metal/coating interface is greater than the one required for corrosion to proceed. His hypothesis was based on the fact that the barrier action could not explain the effectiveness of the coating, while the conductivity of the coating is the main factor controlling the corrosion protection degree offered by the coating. Mayne also reported that when the coating is immersed in a solution, it will gain a certain charge, negative or positive, depending on the nature of the coating. In this case, the coating will allow the opposite charge species to pass through. He believed that the permeation of these species will be through the bulk of the matrix. Cordy attributed that the permeation of such species is affected by the presence of pores or imperfections in the coating. Based on that, he concluded the permeation to be through the pores and voids in the coating. Funke has a different understanding to the way the coating works to protect the steel. He believed that the protection degree that the coating offers depends on the degree of adhesion. The permeation of water through the coating will result in a water accumulation between the substrate and the coating, leading to coating blistering or coating delamination as a result of generating hydroxyl ions as products of the corrosion process. Such ions are believed to break the bond between the coating and the metal surface, and consequently, the coating adhesion will be significantly degraded. Considering all the above approaches, loss of adhesion, the diffusion of water and oxygen, and the transport of the charged species can potentially result in poor corrosion protection performance. In general, mass transfer, diffusion, of a material in a specific environment is a result of a natural process tending to reach equality in concentration between 2 points. In the case of gases, the diffusion process will be mainly based on the difference in partial pressure, which is the driving force pushing the gases from one side to another. In case of polymeric coatings, the diffusion process will mainly depend on 3 factors: the nature of the polymeric coating, the magnitude of the driving force, and the nature of the diffusing species. The general mechanism of the permeability through the coating will follow 3 main steps: solution of small molecules in polymer, migrating through the polymer, and emergence of that molecule at the outer surface. Accordingly, the permeability can be presented mathematically as the product of solubility and diffusion as shown in 1. When a coating is exposed to an electrolyte, the diffusion of the electrolyte follows two processes, which can be classified as fast and slow diffusion. The fast process can occur within a few minutes of exposure, while the slow step can take weeks or months. According to Scantlebury, during the fast process, the electrolyte can reach the surface of the metal, but its electrical properties do not support the corrosion process, while the amount of electrolyte can reduce the adhesion strength of the coating. There are many factors affecting the diffusion of the electrolyte in the corrosive species, namely water and oxygen. Considering the fact that the permeability of a coating depends on the amount of defect present, it can be concluded that the diffusion will be through areas of imperfection. These areas can be considered as free volume, including pores and area of weak cross-linking density. The free volume concentration increases, as the temperature goes above the glass transition temperature, Tg, of the coating. Tg is known as the temperature at which the coating state changes from glassy or solid state to a rubbery state. Above the Tg, the energy of the coating molecules increases, leading to an increase in the movement of these molecules. As a result of this, the free volume can increase, providing more areas for the diffusing species to transport through the coating. Based on that, it is highly recommended to select a coating having Tg higher than the temperature of the process. Film thickness has a great effect on the permeability of the coating. As the film thickness increases, the penetration of the corrosive species through the coating can be delayed. Increasing the film thickness above a critical thickness can increase the probability of having cracks in the coating. Certain pigments have a significant effect on the permeability of coating. It is believed that water and oxygen cannot pass through pigment particles, therefore, the permeability can be reduced with increasing the pigment volume concentration, PVC. The PVC value should not exceed the critical pigment volume concentration, CPVC. Above the value of CPVC, the pigments will introduce voids and gaps inside the coating. These defects can provide an easy way for water and oxygen to go through. It was reported that the pigmentation of inert particles such as nanoclays inside the coating can act as a barrier to reduce the diffusion rate of water and the oxygen through the polymer clay nanocomposite coatings. The nanoclays have evoked a great deal of attention lately for the preparation of novel nanocomposite materials for several applications. The uniform dispersion of the layered silicates into polymers matrix leads to the preparation of nanocomposites with improved mechanical properties, thermal stability, and low flammability. This is attributed to their lamellar structures, which are distinguished by having high in plane strength and stiffness, as well as a high aspect ratio. Additionally, the clays possess excellent stability and low toxicity, and they are cheaper and widely available compared to other non-organic fillers. Such advancement plays a major role in enhancing the coating industry, specifically for corrosion protection. One main factor attributing to coating failure is its inability to maintain low water and oxygen permeability throughout its service life. The penetration of these elements through the coating leads to corrosion initiation under the coating. The addition of clay to polymeric coatings has great potential to improve the corrosion protection performance of the coatings. This lecture will present the recent advancement in the preparation and utilization of polymer clay nanocomposites as enhanced coatings for corrosion protection.